Well, let's get started with another segment. As you know, that I've been accumulating uh, portions of my training program and putting them into smaller segments. So I'm not going to be covering all the information that you'd find. As an example, in the origination of carbon monoxide of clear and present danger, I was fortunate enough to help co-author this publication. The base information that I'm going to be speaking about has come from that publication. Some of you have sent for the booklets that I've used and that I do use in my on-site presentations. They're briefer than this book, but certainly not a replacement. That's Carbon Monoxide Clear and Present Danger is still a good base book for your knowledge of carbon monoxide. The booklet's an abbreviation of that. Your parts per million chart is in the back, so you still have that information. And the things about building pressure and combustion analysis and how many parts per million, fire safety, building pressures. There's information about test instruments, personal monitors, combustion analyzers. We do our best to fulfill the interests and needs. And the main focus here is safety. So if you have any need of any of the written information for your groups, if you would like me to participate online or in person, but online, if you're having a brief meeting, a short meeting, a staff meeting, and if you're using these booklets to try to get this information, say part of your safety classes, I'll be glad to participate. And regardless, there's my email address. Let me know how you're doing with carbon monoxide safety, if nothing else. So this segment, why wait for the alarm? Well, don't. Carbon monoxide's a toxic gas. It acts like a poison, referenced in abbreviation as CO. CO is unhealthy to breathe. Carbon, C, oxygen, that's a molecule derived from two atoms, one carbon atom and one oxygen atom. So CO can injure or kill. It is a byproduct of incomplete combustion. I'm Bob Dwyer, Carbon Monoxide Safety Association, Director of Training. Well, when I first started doing testing, oh gosh, back in the late 1980s, early 1990s, this was the technology that I learned on. The stain tube technology, you would break off the ends of the glass vial and you put it into this suction where you could depress the little plunger there with your thumb, and then when you released it, it drew air in a room. As an example, when you walked into a room inside a building, it would darken that stain to varying degrees depending upon if there was any carbon monoxide and how much was present. And then you would also, depending upon the density of the stain, the length of the stain, you could, on another chart, you could look at how many parts per million of carbon monoxide that was in that room. You could attach a hose and probe assembly and a little aspirator bulb, and you could then use that device to measure carbon monoxide in combustion gases, like in a furnace, how much carbon monoxide was being produced by a furnace. The leak tech device there, you had a little material that was sensitive to carbon monoxide, like in the stain tube, was reactive, changed colors, and in the case of the badge, that was something you wore on your shirt. That was something that you put on your hat, tough on your hat, but it was something you were to look at and pay attention to if you were walking in a space that contained carbon monoxide. Well, that was the early testing devices. We saved lives by utilizing those devices, walking into homes, finding carbon monoxide in airspace, tracking it to what were the combustion sources, and we, through process of testing and elimination, we found sources of why people were having symptoms of illness that they did. We're just amazed at how many times we encountered people utilizing this technology that benefited from us using this technology. Back in 1993, here's a picture of yours truly. This is our local newspaper picked up um, some information based upon a near poisoning that had occurred. I was fortunate enough to be involved with finding that situation and correcting that situation. Not that I corrected that situation, but brought in the responsible parties and contractors and technicians and authorities of jurisdiction. Um, not only do we talk about carbon monoxide, and they're utilizing an electronic test instrument now. It was an um, acid-based electrochemical sensor that was specific to carbon monoxide, and I'm testing under the draft hood of a gas water heater. Well, I'm not just sticking the straight probe up into that airstream, because if this thing's functioning right, air out of the room is going up at that spot to help aid and assist with the temperature and control of the vented products coming out of this gas water heater. I had a little hooked end on that probe, so it was down inside where there was combustion gases, and that was before dilution air that came out of the room that I just described. So taking a test and demonstrating back in 1993 to local heating contractors, the gas utility company, the fire department, and other contractors, that, hey, there's a way that you can walk into a home with this device on. You don't even have to have the hose and probe assembly on when you're walking into a building. And when you walked into a building, you were measuring carbon monoxide. And we found, just like we did with using the stain tube technology, only this was faster and more accurate, and it put it into language we could understand. Parts per million. Out of a million molecules of air, how many parts are CO, or carbon monoxide, in that air? So there was ways that we could measure carbon monoxide. And a newspaper picked up the story, and we did our best with what we had at the time again, and we kept records and found, carbon monoxide poisoning at a church, carbon monoxide at a daycare, carbon monoxide at a school, carbon monoxide at a business, a factory, a warehouse, an electrical supply house, propane forklifts. And again, you walked in, and at one time when you were the only person who was measuring for carbon monoxide, and you were learning as you went, and you were teaching as you went, because nobody was measuring, and yet people were seeing, I work here, I live here, I'm getting sick, and could this be what's causing my chronic illnesses? And we found out that that was the truth. That was, in fact, what was happening. Well, we're not going to wait for an alarm or an injury. We're going to have our own alarm. When we enter a building, we should always have a personal carbon monoxide monitor. It fits in the palm of your hand. It can clip to your shirt. You can wear it on a lanyard around your neck. I wear mine on my belt loop. I always know it's there. I'm always looking for it. When I walk into a building, I just look at it and check. It's become a habit for me. Why? Well, because I have measured carbon monoxide for years and years in a variety of ways. This is about as simple as it can get. And when you're measuring for carbon monoxide, you will find situations that will surprise you and educate you. So entry testing may decrease the frequency of CO poisoning. I'm here to tell you it will decrease the frequency of CO poisoning, and perhaps the continuation of some health symptoms that the homeowner or the resident or the tenant or the visitor in a building, they're not aware that it's carbon monoxide that is causing and contributing to those symptoms. We can't have a lot to say about the collective combustion gases outside of buildings. We don't know where cars are warming up or automobiles are running in herds. So always check outside before you enter a building, particularly if you live in any kind of urban areas. But that's not to say if you're in agriculture, there's a lot of combustion systems in ag buildings, from the small farm to the corporate farms, and construction sites. So, I mean, there's a lot of reasons we should be measuring carbon monoxide everywhere we go. Home inspectors, building inspectors, permit inspections. That's a lot of opportunities. Home health nurses and care providers, daycares. I mean, there's a lot of reasons why maintenance people at motels and others in stores and restaurants. You're responsible for buildings in any capacity. I highly recommend that you measure for carbon monoxide, and hopefully when you save a life, you will be very grateful and thankful that you did that. Well, we need some base information when we're talking about carbon monoxide, so we'll call this Combustion 101 for everyone. Combustion is a chemical reaction that requires heat. Now you're going to find a lot more information about this in the carbon monoxide clear and present danger book and the booklets that you've got. But keep in mind, again, combustion is a chemical reaction that requires heat. So we have to have fuel and air mixing together into fire or an ignition source. Now let's take a look at our air. Our air contains approximately 78%, a little over 78% nitrogen and around 20.9% oxygen, with a few other chemicals in our air. But these are the important ones that we need to be familiar with for combustion. Now our fuel is a hydrocarbon fuel. In this case, it's CH4, 1 carbon and 4 hydrogens. That's the makeup of methane, the predominant gas in natural gas. So in order for our fuel to burn, now fuel by itself won't burn. We have to have specific amounts of oxygen. And depending upon how well it burns, we have to have the precise amount, a very tight range of oxygen with our fuel. Now we also have to have specific amounts of temperature for this to burn completely. So again, in order for us to have heat or to make heat or fire, we have to add heat to the chemicals, the HC fuels and the O's and N's of our air. So we're going to take a closer look at this. Again, carbon monoxide is produced as a result of incomplete combustion, fuel and air properly mixed. We will have limited amounts of carbon monoxide produced. So again, as we've indicated, carbon monoxide is always the first byproduct in combustion, and if that fuel and air mixture in the form of fire, if it can complete its journey and stay contained until all the carbon is burned off and converted to a predominant carbon dioxide, you'll always have carbon dioxide in combustion. But again, combustion is the rapid oxidation of a fuel, and as the fire is burning, it's drawing in air to be mixed with that fuel. So Combustion 101 for everyone, there's our start. Here's a continuation of a simple experiment we've talked about hundreds of times. We have a fuel, we have a candle, we have plenty of air in the room, contains 20.9% oxygen. We are going to provide heat, and in the process of providing heat to light this candle, we have to convert that wax to a gas. So as we apply heat, we hold the lighter over the wick or on the wick. In the process, we are beginning the process of melting wax, converting it to a gas, and the fire is now hovering over the wick. So now there's limited CO production occurring here, but we're going to be taking a closer look at the flame to get a better understanding of fire and carbon monoxide and complete and incomplete combustion. Well, now we have successfully lit the candle. And in the process, and if you get a closer look at that flame, and we'll get a closer look at here in a moment, you can see that it looks like there's nothing right off that wick, and the fire is on top of the wick. It's hovering over the wick. Well, that's where we have gas being produced, and we can't see the gas. But the gas that is being produced and the oxygen from the room is being drawn together because of the action of the heat. It's pulling up, it's pulling air and gas up around the wick, and it's mixing to the explosive level that it needs to generate fire. So if we could keep this contained, we would have a couple hours worth of candlelight. It's not a lot of heat, but it's a little bit of light. Light and heat. Combustion. Here's that closer look at that candle and the fire. You can see that the fire is floating above the wick. You can visualize that the gas is being produced by the melting of the wax. It might be tough to see if you're just looking at it on a phone. If you can get that picture a little bit bigger, you can look at that flame and you can kind of see that it's got a yellow distinct cone right off that vacant looking space around the wick where that invisible gas is. You can see that there's a yellow cone. Now in combustion, everything burns to carbon monoxide first. It's only partially burnt. That's carbon monoxide's unburnt fuel. And you can kind of see that there's a yellow rim around that flame. Well, in the process of combustion, as the gases get hotter, more contained in the fire, then we will burn off carbon monoxide, and one of the byproducts would be CO2. Now there's going to be nitrogen involved in this, but it's not burning, it's just passing through. Nitrogen won't burn. It has another issue where it can combine with oxygen and combustion gases after the fire, but we're not going to talk about that in this brief segment. But the characteristics of fire, everything burns to carbon monoxide. If it's hot enough and contained enough, you can reduce the amount of carbon monoxide that's produced. And of course, the combustion gases should be vented away. And with our candles, we generally don't have a chimney for our candles. And the next step in this little candle demonstration is we'll take a jar and we'll hover it over the top of that candle. And we'll get a closer look at the flame again here in a minute, but our well-defined yellow cone on that flame is flattened out. Instead of drawing air for combustion from around the room right into the fire, now that there's no escape for the combustion gases, and they're now swirling, they're building up, and they're dropping back down around where the air should be from the room that's feeding the fire. Instead, the combustion gases in the jar now are turbulating back down around that flame. And that yellowness now, that yellow, if you could get a test instrument in there and measure the yellow cone from the previous photo or this one, you could measure thousands of parts per million of carbon monoxide. Now keep in mind, this is a small flame, and parts per million from a small flame like this is not going to contaminate the room. When you snuff out the candle, you'll smell the smoke and perhaps see the smoke. And then you could measure a small amount of carbon monoxide from one little candle like this. And that's just because you can pretty near see the unburned fuel floating around the air. But it's important to understand that we need to have oxygen on our combustion systems, whether they be a small candle or, as I said, a 500,000 BTU gas boiler or something in between. And here you can see that the well-defined cone on our flame has flattened out. You can see the combustion gases are taking its toll because they're warm and they're contained in that jar. They're warm and they're melting our candle at a little faster rate. So in this particular case, are we converting more of the candle to gas with not enough oxygen? If we could stick a test probe from our combustion analyzer and test instrument up inside that jar, we would pick up hundreds to thousands of parts per million of carbon monoxide if that's just inside that jar. Again, when we end the experiment and we wave that jar around into the room that we did it in, there was really no measurable parts per million of carbon monoxide. But we had our test instruments on and measuring as always. And just as one of my instructors told me one time, if we had fuel, air, and heat, you take one away and combustion stops. Well, in this particular case, we've just taken that jar now and just put it completely over the candle on the table, and the fire went out. There was no oxygen to feed the fire. It had burned up all the oxygen. Oxygen will burn. Now, all that's left in that jar is the residuals of combustion, some CO2, some carbon monoxide, some nitrogen oxides, and there'll be a film that'll develop on the inside of that jar. I know that because I've done this several times, and you always get a film inside the jar. So why would we wait for a carbon monoxide alarm to find out how many potential sources of CO there are in a building? Did we seal up this house, or did the homeowner or the landlord or the builder seal up this house to make it as tight as a jar? Could we solve one problem and create another one in the process of trying to save energy? How many of our appliances need air for combustion that come from inside the home? More and more gas appliances are drawing air for combustion from outside the building if they're put in sealed combustion units, but there are still very high percentages of gas water heaters and gas furnaces, gas ovens that require air for combustion that comes from inside the building. Some of these have sealed exhaust systems and some of them don't. Some of them are atmospheric, or some of them are directly open to the space, like in a gas cooking oven. It's important to have exhaust fans that exhaust out in gas cooking situations. And there's some good information about some bad information about cooking with gas. We're not going to talk about that. I have measured carbon monoxide in gas ovens over the years, even going back to using the stain tubes, but more often and more accurately when I had the combustion analyzers, the single sensor or the full combustion analyzers that measured more than CO. Take a look at the building that you live in. How many potential sources of carbon monoxide might there be? How about a customer of yours? How about a tenant of yours? How about the building that you work in? What are the potential sources of carbon monoxide? Now, who's responsible for these? If you're in the service business of HVAC, walking in, measuring, having the proper tools for assessment, knowing that you may be there for a furnace, but if your company has proactively worked themselves into a situation where they can provide a whole house carbon monoxide safety inspection as part of that visit. But you better know what you're doing if you're that technician doing it. And if you're a homeowner, You need to know what it entails. It takes education, it takes experience, it takes test instruments. And what those inspectors are doing, they're paying attention to circumstances that could make you unhealthy, um, or worse. So know what the sources are, whether you have a basement, whether you have a shared heating system, whether you have a crawl space underneath the homes, whether or not you have furnaces or water heaters in attics, how many unvented appliances do you have, how close are you to your neighbor's house when they use their barbecue or run their automobile, do you live where parking is underneath you, alongside you, over the top of you? So again, these are things that we need to know. We have to be aware that carbon monoxide can be in a lot of places. Why measure CO every day? Well, where will you be? What will you be working on? And where will you be working? What type of building? What type of combustion systems? What's the mechanical room look like? When you walk in, are people sick or ill? What about traveling or playing, recreating? Um, why shouldn't we measure carbon monoxide there? Some of these motorhomes, some of these RVs, they have multiple sources of combustion gas. And again, the carbon monoxide news stories, every building you see here, every type of RV, carbon monoxide poisoning has occurred, and there's news stories to back that up. So every day is a measurement day, whether you're at work or whether you're at play, recreating. You may be in an apartment complex. You know, carbon monoxide can have one source in an apartment complex, and it can move through walls. It can move through the structure, and the whole place needs to be evacuated. Or it could have multiple sources of carbon monoxide. You are in an RV park and you're enjoying yourself with your family on a vacation or some sort of sporting event, recreational event, and you're parked right next to another RV that may have 4 or 5 sources of combustion gases, plus a barbecue. And in these areas, with more and more of these systems having generators for people to have electricity on site and air conditioning on site, these combustion gases can infiltrate into yours and throughout the complex. So keep in mind, uh, when you're asking yourself, well, why do I need to measure CO every day? If you don't measure, you don't know. Well, this is a slide for my mechanical inspector colleagues and friends. Thanks for communicating with me when you do. It's always good hearing from you and sharing circumstances that you encounter. Um, you know, the headline on this, the June 3rd to 15, 2020 from the Carbon Monoxide News that I posted, gas furnace not sealed to the platform, from the Chicago Daily Herald. Well, in that particular case, there was a poisoning that occurred, and I could certainly relate to it. This was a photo I took several years before then. Um, this was a warm summer day in a warm climate, 90 degrees outside. Um, the family had been poisoned by this system. What you don't see in the picture, and it's the same appliance that we're looking at. The one with just a regular camera, the one on the right with infrared attachment to my cell phone, so a thermal imager. You could determine the temperature of the air and the components. The blue represents cool air in this room, or something cool. The yellow, the darker the yellow, the warmer the system. The air conditioner was running on the thermal imaging system on the right. And what's important here is that to understand the impact of an unsealed furnace forced air fan system. One, it can, if it's not sealed, um, you can actually draw air into the return system right out of the mechanical room. Now this is an upflow furnace. It's sitting on a box, and this box is the return air plenum. And the return air grate out of the living area is off to the right of this box as we're facing it here. And it's running on this warm day, and you can see the blue is leaking out the sides, particularly on the left side as we're facing it here. And you don't see any blue in the very front. Well, that's because, first off, the mechanical room door is wide open. And with this door being wide open, one, it's tough to really get actual operating conditions. There's just tight space. There's no room for anyone to sit in there and do this. Now, using Bluetooth technology systems, you can close the door and you can run tests on the furnace and the air pressures within this mechanical room closet. Now, this mechanical room, it really didn't have a lot of combustion air for two appliances. It had a 6x8 louvered and screened grate in the door, and that was it. It was really getting air from itself in this room. The air handler, when it was running on the furnace, you can see again there's no leakage out of the furnace in the front. It's drawing air in, and you just visualize with the door closed, it was perhaps drawing some outside air from that 6x8 louvered vent, or it was pulling air right out of the mechanical room. Now, these furnaces require a lot of air for combustion, and they require air for movement, but the movement of heated air or cooled air shouldn't come out of the mechanical room or a crawl space. So ducts need to be sealed, and the starting point is with the furnace being sealed on a forced air system. Now, the water heater, standing on with a standing pilot light, it had a tough time venting or removing the combustion gases from a small pilot light up and out of the system. But when it fired, if the furnace was on or the air handler was on, moving air inside the building through this system, that's what they do, then it certainly struggled. The gas water heater struggled with venting. And because the air fuel mixture at the burner of the water heater was really interrupted by this powerful forced air system in operation on the furnace, the air fuel mixtures weren't correct, and the likelihood and the production of carbon monoxide increases. And so now, if it's not venting properly and it's now producing more carbon monoxide because of this, it's being drawn into this upflow furnace and being delivered to the rest of the building. So it's important that we get these furnaces sealed to the floor. It's important that we have enough makeup air or combustion air for these systems, and that the homeowner understands that this equipment needs to be installed properly to follow manufacturer specifications at installation, and that they need to be serviced at least minimally once a year. And once a year, they need to be inspected by someone who has test instruments. They have a full understanding of how equipment can produce carbon monoxide and how they can help prevent carbon monoxide from even being generated by the combustion systems that they're servicing. On new installations, we got to make sure that we're pulling permits and that we're having them inspected. And not only are they inspected, but they're tested to be performing the way the manufacturer intended them to perform. It's important. Sealing the furnaces of forced air ducted systems, they must be sealed to the floor as the manufacturer has indicated. Well, record keeping is important. Here's a form that we have in the back of our books. You can, if you need them, you can contact me, and we'll make sure that you get them if you can't find them online. There's a variety of tests that need to be performed and some demographic information about the location of the building. Well, importantly, how much carbon monoxide was outside before you entered, how much inside. Do they have working smoke alarms and detectors? Do they have carbon monoxide alarms or detectors? Was this a poisoning incident or was this a service incident? If it was a poisoning incident, or if you detected carbon monoxide, if you have a device to measure carbon monoxide in breath or with a pulse CO oximeter, then that particular test can be taken. You take a look at the listing of all the appliances that are in the building, and do they have an attached garage? Do they have a tuck under garage? Do they have a barbecue system that's adjacent to the house? Do they have a fireplace? Do they have a carport? Some very base information, demographics that we need, as well as testing results. There's space on this form for taking tests regarding the building pressures and the duct systems. Is there any sign of duct leakage? Is there any sign of appliance failures in venting when we turn on exhaust fans or close bedroom doors if there's only supply duct systems to those bedrooms and we have a common return in the hallway? So documentation is vital, and let's make sure that we're keeping good records, whether we do it on paper or we do it on an app. Well, here's a little scenario. You just walked into a house and your personal CO monitor sounded off as it rose over 25 parts per million. That's what you have it set at. And it's now reading 33 parts per million. Your customer's CO alarm is silent. Well, when should you call the fire department? Do you know when the fire department puts on their breathing apparatus? Do you know when they begin their civilian evacuations? You should know it. You're a professional. With the fire department, when do you put your breathing apparatus on? Now let's keep in mind that there's some fire departments out there that still may not be measuring carbon monoxide in every call. They may have to run back out to their truck to get their test instrument. If they have one there, they may have to call in to command and get that test instrument there. EMTs, it's over the years, I've watched them go from not having personal CO monitors to not even considering entering a building on a medical call without a CO monitor. They have them on their ready packs if they're not wearing them. So it's very important. So what would you do? Well, personally, knowing where I live and I know what the fire department responds to, I would call the fire department and let them know that, and I would let my customer know, hey, you've got an issue. I need to have it documented that this is what I walked in on, and it's very important for you and for your safety. Maybe they'll show us something that we're unaware of. So it's important that we have a good working relationship with the fire department. In the classroom, to me, some of the best classes have been conducted in conjunction with a visiting safety instructor from your local fire department. They can go over some things and demonstrate to your students or to your group about fire extinguishers, the need for them, smoke alarms, carbon monoxide detectors. It's very important that you include them if you're in a school, to have them on some of your committees, your technical committees. It's part of the community. I think it'd be well worth all the community's whiles. So why wait for the alarm or injury? Well, here's a lot of different reasons. 5 children, 3 adults taken to a hospital following carbon monoxide alarm in Bay Meadows area. That's in actionnewsjacks.com. Scary incident in Greensport. Family treated for carbon monoxide poisoning, from a story from KFI AM 640. 3 found dead in a home, from the Crossville Chronicle. 7 workers suffered carbon monoxide poisoning in a business near Morgantown. Article out of WFMZ Allentown. Troy firefighters, residents hospitalized for CO poisoning, from WNYT. Man exposed to carbon monoxide recalls waking up to police at his door, from KXLH Helena News. and woman dies of carbon monoxide poisoning, posted in ANSA. Well, don't let these be your carbon monoxide alarms. I can't stress the importance of being diligent about carbon monoxide and testing. Reduce the number of ambulance calls and ER calls. If you're on that call, have your personal CO monitors on. Um, Unfortunately, people will die, and people are still dying. I've been looking at carbon monoxide news stories ever since the 1980s, late 1980s, and almost daily whenever I can now online. And you can't let these be your carbon monoxide alarms. I've been involved as an expert witness in carbon monoxide lawsuits. It's not fun work at all. So let's be responsible for the air that we breathe, and let's measure carbon monoxide everywhere we go. So this is just a part of the carbon monoxide safety series. Detectors, not all CO detectors are the same. Technicians are detectives of CO safety. They too are detectors. Not all CO detectives are the same either. So it's important that we understand test instruments that we have, the ones that are out there in the field. Many kinds of detectors. Some are for air only. Some are old, new, still in development. This collection on the left, that's mine over the years, and some I'm using today. The pictures on the right, you can go to hardware stores and home improvement stores. You can buy them online. You can buy carbon monoxide and smoke alarm combinations. You can buy carbon monoxide alarm that also tells you what the temperature is. Now, that's a little confusing to me that you'd always have a number on there. But in any case, individual CO detectors, high-level detectors are most of these that you see in that picture. They don't go off at their lowest end until it reaches 70 parts per million, and it has to be over 70 for an hour. Then it can take up to 4 hours for it to sound off. Now, if you look at the information about those alarms, though, that's what it'll tell you. Those are the test points. That's the lowest test point in parts per million. So it takes between 1 and 4 hours for you to be alert to, say, 80 parts per million. Now, there are low-level detectors. I've got one pictured there. That particular model goes off as soon as the levels get above 10 parts per million, and you'll know that within a minute. There's oftentimes I've used that and walked into a building or been into an airspace where all of a sudden, within a matter of moments, up to a minute, it'll go off and I'm reading 33 parts per million. It bypassed the 10. I didn't pay any attention to it until it made a sound, and then other than just when I first walked in and I saw, perhaps a 0 as I entered the space. But as farther I got into the building, so it will alert you in very brief periods of time, just like the personal monitors will as well. So know what's out there, know what your customers have, know what they don't have, find out how they're testing them. Some you can put real gas on. You can buy canisters of carbon monoxide gas. So what you provide for yourself in understanding carbon monoxide in your own homes and buildings, for your employees, or for you in providing service. Like I said, some of these instruments and monitors, you can get a canister of carbon monoxide gas. You can put them in a plastic bag. You can put them in little clear containers. They're easy enough to get. Food products, once those plastic containers are cleaned out, it's very easy to rig up a little test chamber of various sizes. That's how you learn about carbon monoxide test instruments and their reaction time. So low-level detection is vital. Here's an ad to kind of prove that. I posted it on the Carbon Monoxide News, January 22nd of 2017, where Fire and EMS adds new tool to life-saving arsenal. And the chief explains, we go on 2,900 calls a year. That's 2,900 times we can monitor homes. That's amazing. So they understand that the more you test, the more they're going to save. That's vital. That's really important for us as we move through, and as that way we're not guessing and not chasing things that are just become guesswork. So carbon monoxide's odorless, tasteless, it's invisible. So don't chase the ghost, walk in measuring. That's very, very important. So as we take a look at these segments, every part of what I have to offer to you is a hope that you'll start measuring, and a hope that when you measure carbon monoxide and you find you've had an impact, that you keep doing it and try to encourage other people to measure for carbon monoxide. Preventing carbon monoxide poisoning, whatever you do, wherever you are, we're all vulnerable. Prevention before rescue, raise awareness, save lives. Thank you.
Carbon Monoxide, A Clear and Present Danger was a book published back in 2003. I was very fortunate to be part of that project. The science hasn't changed. This slide presentation and my discussion is going to rely on a variation of that basic science that's still found in that publication. It's a great book for learning the language, and again, the science doesn't change. In this program, we're going to continue to discover more about carbon monoxide. What does CO mean? One carbon atom and one oxygen atom bound together, forming the molecule carbon monoxide? Well, there's a starting point. How do you detect it? How do you measure it? What are the health effects? How much is too much? What can we do to prevent it? What are the educational opportunities? Well, it all comes down to measurement. Without measurement, it becomes guesswork. And that's when carbon monoxide can have its biggest impact, when we're not taking it seriously. So carbon monoxide is something we're going to take serious. I hope you take it seriously too. Let's take a look at the next slide.
I'm Bob Dwyer, Carbon Monoxide Safety Association. Don't wait for the alarm. Don't wait for the injury. You be the alarm, and you prevent the injury.